palladium silica catalyst, the effective pretreatment and of calcium to palladium ratio. The authors are Bonivardi, Chiravasa, and Baltanas, and the presenter will be Dr. Bonivardi.
The title of this work is Methanol Synthesis on Calcium Palladium Silica Catalyst, and I will try to emphasize the effect of the pretreatment or method of preparation in the calcium to palladium ratio of our catalyst in the methanol synthesis. I also want to say now that this work was done in the Instituto de Desarrollo Tecnológico para la Industria Química in Santa Fe, Argentina. We know that industrially methanol is produced using synthesis gas containing CO, SiiO2, and hydrogen, and using a copper synoxide aluminum catalyst at about 513 Kelvin at 5 megapascal. But in 1978, palladium appeared as a possible alternative to the conventional copper-based catalyst to produce methanol from CO and hydrogen. At that time, Postman reported that they were able to produce methanol at high selectivity using palladium supported on silica. After that, several works have been done trying to increase the activity and the selectivity of those catalysts. As an example, alkaline earth and rare earth elements have been found to be promoters of that synthesis. Even when it is difficult to compare results obtained under different experimental conditions, magnesium, calcium, and lanthanum seems to be the most promising promoters for the methanol synthesis. And keeping in mind that palladium on silica could be an alternative to the conventional copper-based catalyst, we choose the calcium-promoting palladium silica catalyst instead of magnesium and lanthanum because calcium is the least studied. The experimental part of this work, let me start with the catalyst preparations. We choose palladium acetate as a promoter rather than palladium chloride in order to avoid any possible chloride promotion. And we use well-purified Davidson grade 59 silica shell that was washed with different organic solvent and nitric acid solution in order to remove impurities. Then we dissolve the palladium acetate in an ammonium hydroxide solution at pH 11 and mix it with the silica. Under those conditions, tetramine palladium underwent ion exchange over the surface of the silica, and upon drying in air at 423 Kelvin, which is about 150 degrees C, during 2 hours, palladium diamine remains over the surface of the silica. After that, this material was split into 2 fractions. One of the fractions was reduced in hydrogen at 450 degrees C during 2 hours to give a reduced palladium on silica. The other fraction was used without any further treatment before the addition of calcium. The incipient Western impregnation method was used to add calcium to both fractions. This involved the addition of a solution of calcium acetate to both fractions. In that way, we obtain 2 series. Series R that comes from reduced palladium, and series S that comes from unreduced diamine palladium. Then, both series received the same treatment. Water was removed by sublimation after freezing the samples. Then the samples were calcined in air at 400 degrees C during 2 hours, following by reduction in hydrogen at 450 degrees C, also during 2 hours. And finally, the samples were passivated with a mixture of oxygen and nitrogen before being removed from the glass reactor. The catalyst evaluation was done in a copper-plated plug flow microreactor, which was operated differentially. In a typical experiment, we charged the reactor with a passivated sample, flushed with nitrogen, and then reduced with hydrogen at 1 atmosphere and 250 degrees C. After that, the reactor was pressurized up to 3 megapascal and fed with a mixture of hydrogen and CO. The ratio of hydrogen to CO that we used was 2.5. The pressure was kept up to 3 megapascal, and the temperature varied between 493 to 523 Kelvin in order to determine the activation energy. The space velocity was 20,000 per hour. The effluent gas was analyzed for methanol, dimethyl ether, methane, C2, C3, CO, SiiO2, and water. We reached a pseudo-steady state for all the samples after 20 hours of reaction, where the total conversion of CO was always less than 1%. As an example, in the figure below shows the activity versus time behavior for the sample S5 that we define later on. We define the pseudo-steady state to occur when the difference between two consecutive rate measures was less than 1%. Samples were taken every hour. Then this curve flattened out, and the decrease in activity was only 1% after 50 hours of reaction. Also, I want to say here that all the results that I'm going to report about activity and selectivity correspond to this pseudo-steady state. This table summarized the characterization, results, and coding of the catalyst, where R stands for series R and S stands for series S. Basically, all these catalysts have the same palladium loading, which is 2 weight%. They have the same average palladium particle diameter of 14 to 15 angstrom measured by TEM. Also, they have the same BET surface area, which is 260 for most of the sample, and the same pore size, which is 170 more or less. They are also the same at the surface areas and the pore size of the support. So, I want to point out that the difference between these samples is the calcium to palladium atomic ratio that goes from 0 to 2 in the case of series R, and the same for series S. The other difference was for samples S3, S4, and S5, where some big particles or agglomerates of about 30 to 40 angstrom were observed in the TEM micrograph, even when the average palladium particle size was centered around 14 to 15 angstroms. Now, these are the results of initial rate to methanol in mole of product per gram of catalyst per second versus the calcium to palladium atomic ratio for series R in the experimental conditions that I previously described. This pattern of activity has the following characteristics. First, the activity goes up as we increase the calcium to palladium atomic ratio, and then goes down. Since calcium was added in this series over the pre-reduced palladium, we can speculate that this maximum is due to two effects. The first effect could be the promotional effect of palladium by calcium at lower calcium coverage. And then the other effect is the active site blocking by calcium as we add more and more calcium over our sample. But we don't understand what is the nature of this promotional effect. Anyway, to convince you that this is a real pattern, I want to compare now our result with the result reported by Kaiser. The green curve. Kaiser reported their result working with a catalyst prepared with calcium chloride and palladium chloride solution, mix it with silicon, then they decompose it, reduce their catalyst. And their experimental condition for the reaction were a ratio of hydrogen to CO equal to 3, the temperature was 300 degrees C, and the pressure was 17.2 megapascal. The phase velocity was the same as our value. As you can see, these patterns are pretty similar. These are the result of initial rate of methanol, again versus the calcium to palladium ratio for both series R and series S. Let me just to remind you that series R, the one that comes from reduced palladium, has a maximum of activity which is twice of that of the unpromoted catalyst. Conversely, for series S, the one that comes from unreduced diamine palladium, the activity rises as we increase the calcium to palladium ratio. And for the sample S5, the one that is here, the activity was greater than 24 respect to the unpromoted catalyst. I just want to remind you also that, for example, these are the sample S3, S4, okay, this again S5, the sample that have these few but big agglomerates of about 30 to 40 angstroms. This table summarizes the results of selectivity and activation energy to methanol versus the calcium to palladium ratio for both series R and series S. We can see that the addition of calcium produces an improvement of the selectivity to methanol for both series. In the case of series R, this improvement goes from 90 to 95, 96%. And in the case of series S, the improvement goes from 84 to 89, 99%. In the case of the activation energy, this value is centered around 100 kilojoules per mole and was the same for the unpromoted and promoted samples, and also is the same, almost the same for both series. So maybe we can speculate that the mechanism for methanol synthesis is not changing. The main byproduct of the reaction was methane, and these are the result of selectivity to methane for both series as a function of the calcium that was added. In both series, the addition of calcium produced a decreasing of the selectivity to methane, that in the case of series R, for the unpromoted sample, the selectivity was about 8%, and then goes down, and it's almost the same for all the samples of the series, and it's about 4%. In series S, these values are going down from the sample S1. For the highest calcium to palladium ratio, the selectivity was less than 1%. In the case of the unpromoted sample, the selectivity was 12%. Quickly, I want to show you the selectivity to SiiO2, ethane and ethylene, and SiiO3, propane and propylene. Again, calcium produced or suppressed the production of hydrocarbons over both series. And these are the results of selectivities to dimethyl ether, ethanol, and SiiO2 that were detected only for series S. In that case, dimethyl ether was observed only in samples S3, S4, and S5, and a little bit of ethanol was obtained with sample S5. Also, we observed SiiO2. Finally, the conclusions of this work are: the activity to methanol on calcium to palladium silica catalyst strongly depends on the preparation method of the material. The series S is much more active than series R. And it is clear also that calcium improves the selectivity to methanol of the palladium silica system, and series S is more selective than series R. Also, the product distribution changes at higher calcium levels. Finally, I want to thank the co-author of this work, Miguel Baltanás and Dante Chiavasa, and I want to thank the group of the technicians, Pedro López, José Luis Xombi, Juan Carlos Chicuto, and Adolfo Larese, that help us in different steps of this project. The financial support of this work was provided by the Consejo Nacional de Investigaciones Científicas y Técnicas and the Universidad Nacional del Litoral of Argentina. Thank you.
From your first slide, I think that you are waiting for this question: what is the effect of SiiO2 on your catalyst?
We have some results about what is going on when we put SiiO2 into the when we fed the reactor with CO, CO2, and hydrogen. In that case, I don't want to talk about that because that is the work of Chiavasa. In that case, the selectivity to methanol goes down. That is the only thing that I can tell you. The activity is for series S is higher than for series R, but it's not the same activity that we saw here. It's lower.
It's lower.
Yeah.
There are some theories that the effect of that promoter is to stabilize palladium ions, and people like Bonitz show that that is extractable with acetyl-acetonate at the end of the catalytic run. Have you tried to detect any extractable palladium?
Yeah. These are the only XPS results that I have of the sample, for the sample S5. These are the XPS spectrum for the sample. I think that you remember that was the most. Okay. This was the S5, no? And the position of the palladium peak 3D is 335 when we don't do any treatment over the sample. Is 335.1 when we reduce the sample at 10 to the minus 5 torr in hydrogen during 30 minutes at 250 degrees C. And it's the same value when we reduce the catalyst, more drastic conditions, which is similar to palladium as a metal than to palladium oxide. So, also, there is a paper of Shen where et al. That they reported that, for example, in the case of magnesium, they were able to see palladium delta plus, but not for calcium. So I think that most of the palladium is reduced palladium in our samples.
And you did not try any extraction by some solvent?
No.
And the calcium, is calcium carbonate at the end?
There is a problem. Padeste, for example, reported that when you decompose calcium carbonate in the presence of palladium, you can decompose this carbonate to calcium oxide in the presence of hydrogen. But the temperature that you need should be higher than 500 degrees C. So, keeping in mind that, for example, in this case, calcium acetate in air, it is decomposed to calcium carbonate. Probably most of our calcium is calcium carbonate.
Adrian, if it is palladium metal, have you measured the number of exposed palladium by some titration technique?
Not yet. Not yet.
Yes, you showed that at certain conditions you had a rather high hydrocarbon formation, which means that you either must produce water or carbon dioxide. And you only showed carbon dioxide production in the case of S5, the S5 sample. But since let's assume you are forming water, is there some sort of water gas shift reaction taking place on the catalyst, or has there no activity for that?
Okay. We couldn't detect any amount of water in these conditions, but feeding the reactor with a pure mixture of SiiO2 and hydrogen alone, most of the products are SiiO2 and water. So I don't know if that answers your question.
Go ahead.
Did you make an attempt to measure the level of interaction between the calcium and palladium in the catalyst prepared from both series?
I intend to measure what the interaction.
Yeah, the level of the interaction.
What we are doing now is trying to get XPS of all the samples and trying to correlate that with the activity of the samples. We also are trying to do some exact measurements to know more about what is going on over these samples. I think that is going to give us some hints about what is the interaction between calcium and palladium.
Yeah, so I think that this might have something to do with your increase in methanol production, because I think we should expect less interaction in the impregnation method.
In what series R than in series S?
Yeah.
Both are air impregnation, but in one case was calcium was added over reduced palladium, and the other case was added over diamine palladium.
Right. But in the series R, you have already formed the reduced palladium on the surface.
Yeah. So the interaction could be different. Yeah, for sure.
One last question, Professor Chikara.
You found the different trends of the calcium promotion for the series of R and C. How do you think about the role of the calcium to stabilize the oxidative palladium, which is an active species for the methanol synthesis?
I didn't see any oxidating palladium of the sample S5. So I think it's really dangerous to speculate more with the results that I have. So I think that we should do more characterization before speculating more about this. I think that is my best answer for your question.
Okay, thank
Yes.
you very much.